Welcome back to another Ramda JS video, and in this video we are going to talk about the good old function filter. And it seems to me that when you are first learning functional programming or functional programming concepts, filter is one of these very early functions that you tend to learn. So if you're already intimately familiar with filter, feel free to skip this video. We're going to try to talk a bit about the Fantasyland specification, and I'm going to implement filter for a maybe data type. And we'll build a maybe data type, and then we'll implement that as a filterable. So if that sounds interesting, maybe stick around or maybe skip forward inside of this video. But if you understand that as well, feel free to skip to the next video. But anyways, let's get into this. So again, filter is one of these very early functions. So it seems to me that the first functional programming function that people tend to learn is map, right? I mean, same thing for me. It's like you come across this concept of map, like people use map, or somebody convinces you that like you have to use map, stop using for each, it's trivial to use map, and then you sort of start to unfold that, and you're like, well, actually, this is fairly simple when you grasp it, right? After you've grasped it, and then you start to use it, and you're like, well, this is clearly better, right? Like, it's sort of self-evident when you've used map that it's clearly better, when you've really sort of understood how to use map. And then you keep moving on to these sort of very basic functions, and then maybe you get into reduce, or maybe you get into one of these sort of, let's say, utility functions first, such as, for example, filter, or find, or reject, or I don't know, something like that, right? And I mean, if you're from a .NET background, you might have used link, for example, and then I think, is it called select filter, maybe? Maybe it's actually called filter. Maybe select is find. I'm a bit confused now. Maybe select is actually map. That makes no sense. Maybe it does make sense. Anyways. But anyways, I mean, if you come from a link background, then I would assume that before, I mean, that's me being prejudiced, right? But I would guess that it's probable that if somebody sort of practically introduced you to link, then you might approach these functions as just practical tools rather than as sort of theoretically studyable functional programming functions, which makes perfect sense, right? I mean, it's like, actually, so maybe I lied a bit about map, right? I did use link a tad before I actually started to think about map in, for example, JavaScript. So yeah, I mean, regardless, let's skip the theoretical parts, right? Regardless of sort of the way you enter into functional programming discussions, filter is one of these things that just tend to crop up, right? Because it's a really good example, and everybody understands the idea of a filter. So like, what is the function filter? Well, it's pretty simple, right? It's like you have a list. Let's jump into Vim here, and let's open up a main.js file, and let's say R is equal to require Ramda, right? Just so we have R, we have Ramda, and then we can start to type out some codes. Like, let's say you have some list, right? You have some const called x's, and then you have this list of like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say, right? Maybe it should actually be, let's exchange the 10 for 0. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we have this list of x's, and then if we want to apply a filter to this, what we could do, actually, like, JavaScript has a native filter function, right? You can say x's.filter, and then you can pass a function here. And actually, if we Google for filter JavaScript, you can see that we'll be able to find here Mozilla docs for the filter function, right? And actually, here they say, okay, the filter method creates a new array. Yeah, actually, sorry, method rather than function here, because this is something that lives on an object. So the filter method creates a new array with all elements that pass the test implemented by the provided function. So the test is also known as a predicate, right? It's like we're saying, I want to have these x's, but I don't necessarily want all of the x's. I want you to construct a new I want you to construct a new list containing all of the elements that match the given predicate that I'm supplying, right? And the predicate is what they refer to here as the provided function. But we could also think about it as a predicate, right? A predicate is a function that, when given some value, returns either true or false. Then that's a predicate, right? Like, that's, if I'm not mistaken, like, that's just a general definition of a predicate. A function that returns true or false, like a Boolean, when given some value. And so that's what we do with filter. We say we have this structure that's filterable, and an array is filterable. A list is filterable. You could say that objects are filterable, right? But we'll get to that. But let's say an array is filterable, because so what we do is that we say filter this array, and I'll pass a predicate function, and I want to have back only the items that return true when ran through this filter. And let me just check in Ramda. Maybe they've also implemented reject. Yeah, reject, right? So let me just click here, reject. You can see, notice the type definition here of reject. We haven't talked about the type definition of filter either, but let's just look at this, and as I jump backwards, you can see it's the same one. Filter, reject. Filter, reject. Same thing, right? I mean, because these are essentially the same thing. It's just that, so filter, what I should say is, reject is filter, but where the predicate is also ran through not, or you could say is composed with not, right? So it's the predicate after, no, sorry, the other way around, not after the predicate. So they're running your predicate and then they're inversing the value. Is that actually, sorry, if it was passed to filter, right? So if we think about reject in terms of, now making it overly or unnecessarily complicated, right? But if we're thinking about filter in terms, or if we're thinking about reject in terms of filter, then reject is filter where your predicate is inversed. So we're saying return everything that does not match, or that returns false when given this particular predicate. So in other words, the predicate expresses, like if the predicate returns true for some given value, then that means that that particular value should be rejected as opposed to as being accepted, right? So if we think about it that way, maybe the opposite of reject should be called accept. So maybe then filter should be called accept. But I mean, filter is a pretty good name, and it's fairly like well used, right? So how would we express this, right? It's like, let's just use plain JavaScript for now. So if we have this list of x's, right? And then we say .filter, and then we pass this, we just inline this function. So let's say for any given x, if the x is, let's say, greater than 5, then that's our predicate, right? This is our predicate. What I'm highlighting now, that's our predicate. And if that thing returns true, then that means that the element, that we will keep that particular element in the list, in the new list that will return. So let me just map a keystroke to running this file through Node. And then let's run that and see what we get. Actually, sorry, I have to, of course, console log this. So maybe we should do this. Maybe I should first console log the x's, and then we'll console log this filtering, or this filter applied to the x's. Whoops. Actually, I mapped incorrectly because I forgot to run this through the terminal. So let me just redo the mapping like that. Okay, let's run. So then you can see that we first have the original list, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have the filtered list, which is 6, 7, 8, 9 only. And it's not mutating the old list, we're getting back a new list. And again, this new list, 6, 7, 8, 9, that we get that list because every item in that list is an item that matches, or that satisfies the predicate x needs to be greater than 5. Right? And I mean, if we would jumble up the order of these values, right? Like, let's say we have 1, 4, 7, 2, 3, maybe duplicates even, 2, 1, 0, 88, 43, 12, 2, 3, 7, let's say, right? What if we have that list and we run it again? Then you can see, okay, we get the whole list back here first when we're just console logging it, and then we get all of the items that are greater than 5 when we're filtering, right? Because we're running that predicate. And of course, just to make this extremely clear, what we could do is we could, of course, say, let's say that we have, let me just call it P, right, for predicate. So we construct a variable called P, and P will be a function where that's expressed like this, right? Given some x, if that x is greater than 5, then the predicate is true. And then we could, of course, just filter using this predicate rather than inlining a function, right? So if we run that, you can see it works the same way. We get the same thing. So it doesn't matter, right? Do you want to inline the function, or do you want to have the function in a variable? Now, okay. So now we've just, like, this is just plain JavaScript. Now the issue with this is that when you have methods like this, they are difficult to compose, right? And this is why, at least in my mind, let me know if I'm mistaken, but this is why it's very, very easy. I mean, it's maybe I should put it that way. There are pros and cons, right? Because when you have methods on objects, that means you can do dynamic dispatching. You can have, or dynamic dispatch, I should say. So like, you don't know what kind of object you have, but you will just assume that it's something which is filterable, and then you'll call filter, right? So that's kind of analogous to the idea of when you have a function that takes the data structure as the last argument, and then you just assume that that last argument satisfies the structure or the interface filterable, and then instead of just calling filter on that thing, you would filter, right? But of course, I think I'm making this more confusing than it has to be, so I think I'm gonna just like sort of skip this explanation. But of course, when we're sort of here, like in Ramda, for example, we're kind of mixing object syntax and sort of function syntax, because we need to use dynamic dispatch in order to implement these things, whereas in a language like, for example, Haskell, you could use pattern matching, but we don't really have pattern matching in JavaScript in that way. So sorry, now I'm off topic. Let's ignore that discussion. If that doesn't make any sense, put that in a box and then just like say whatever. That's not relevant for now. This was me going on a tangent. So what I'm trying to get at is that you could think about this two ways, right? Either you have the array, and then like, let's say like what we called x's, right? So I mean, not like the data structure array, I mean any particular array, but let's call them x's, right? So either you say x's.filter and then you pass the predicate, right? So maybe I should say, let's say list instead. So you say list.filter and then you pass the predicate. Or you can have a function called filter that you first pass the predicate to and then you pass the list, right? And the first one here is the native, sort of native JS approach. And the second one here is, of course, the Ramda approach, right? Because that's the way we do it in Ramda. Because then you have the power of currying, or it's a curried function, so you have the power of partial application. And you can compose this function very, very easily, right? Using pipe or using compose. Now, I mean, as a side note, I tend to mention in some of the videos that these are really sort of not correspond. I'm struggling for a word here, but no, I can't remember. But maybe like duals. I don't know if I'm using that word incorrectly. These two things are very, very, very similar, right? And you can actually think. I like to think about an object as a partially applied function, right? Because in some sense that's what it is, right? It's like you have this list object, so it's like a filter function that's already been partially applied with the list, right? Whereas if you would partially apply, it's like you would do something like this. You would say filter where I don't know this argument, this syntax we've talked about in previous episodes, but I know the list. Right? If this doesn't make any sense to you, and if you've just jumped into this video without watching any of the previous videos, then maybe watch that R.__ video on in Ramda. Maybe watch the curry video in this super long series. But anyways, let's keep moving. So that was just a side, like theoretical side comment. I think it's interesting to reflect over the similarities, like the very, very strong similarities between object construction, like running a constructor, and partially applying a function. In my mind, they're sort of actually basically the same thing, right? But we'll talk about that some other time. So yeah, these two syntaxes, right? The first one is native JS, and the second one is not Ramda. I mean, this would be Ramda, but it's sort of, let's say, functional style JS, more like than more. So instead of native JS here, I would maybe say OOP style JS, right? So Ramda gives us this second function. So let's just move into that, right? So what they're saying, let's read the type definition. They're saying, assuming that you have some f which satisfies the interface filterable, then when given a function that when given some a returns a boolean, so that's a predicate, right? We're just saying, assume there's a type called a. We haven't bound a to any particular kind of interface, or we haven't constrained a to any particular type of interface. So a could be like anything. We're just saying, like, there's this hypothetical set of types called a. And when you have this function that maps from a to boolean, and if you supply that function, and then you supply a container of a such that the container is filterable, right? Because we're saying f of a. So an a inside an f where this f is filterable. We'll talk about what being filterable means. Well, if you do supply those two things, then you'll get back a new f of a new filterable of a, right? But that's just the type definition, right? So let's try to figure out, let's read the definition here. So what they're saying is that filter takes a predicate and a filterable, right? First the predicate and then the filterable, and returns a new filterable of the same type, as we can see here in the type definition, right? F of a to f of a, of the same type containing the members of the given filterable which satisfy the given predicate. So this is, I mean, like, notice how it's sort of exactly the same thing we said in the beginning about lists, but they're expressing it more generally. They're saying, let's not talk about lists. Let's talk about things, or arrays, right? Let's talk about things that are filterable. Now, one example of a filterable is a list. One example of a filterable is an array. But hypothetically, another example of a filterable would be a set, right? Why wouldn't you be able to filter a set? So remember, I mean, when we've talked about sets before in this series, we've talked about sets as things that, like, essentially are a list, but where order is unrestricted, or like non-guaranteed, right? You can't guarantee that you'll get the same element at all times when you're asking for something under an index. But so a set contains a bunch of items, but it doesn't contain duplicated items. So if you have, like, think about our list up here. Let's see, we have 2 here, the number 2 here, and we have the number 2 here. So that means we're actually duplicating the number 2. So that's an invalid set, right? From a set perspective, we should just have a single 2 in that set, because, like, it doesn't matter. If you have 2 in the set, you have 2 in the set, right? But what I'm saying is that a set is also filterable. Theoretically, right? You could say, well, if I have this set of things, like if I have the set of the numbers 1, 2, 3, and I say filter this set such that I get a new set back that only contains the things that are greater than 2, well, then I get back a set containing just the number 3. Right? That's of course a valid implementation of filter for a set. So if you think about that in an object-oriented sense, then it's like there's this interface called filterable, and sets implement filterable, and lists implement filterable, or rather maybe arrays implement filterable, and so forth. And then you can think about a bunch of different things that implement filterable. And that's like, if you get that, then you're definitely getting this sort of constrained notation, because that's exactly what we're saying here, right? We're just saying that this thing f is a structure that corresponds to the interface filterable, or that implements the interface filterable. And sorry. And now, yeah, in JavaScript, it happens to be such that if you have some f of a, if you have some f that is filterable, it respects the interface filterable, then it will implement the filter method, right? Because we're, again, like back to that discussion, we're using object-oriented constructs to define to handle dynamic dispatch, or to determine what thing we're actually supposed to dispatch to, or which path we're about to take, which path we should take through a program. So, but in a language such as, for example, Haskell, or something that has pattern matching, then you wouldn't need to say that f is a structure that implements functions on a sort of object level. Instead, you can say f is a function that f is a type that, now I'm getting a bit confused myself. What I mean is, so let's say f is filterable, then that means that if you have, yeah, okay, I'm sort of confusing myself and thinking about two syntaxes at the same time. What it means is that if you do something like ad hoc polymorphism, then you define the function filter for a particular instance of filterable over some. Wait, I just confused myself heavily, right? This is the problem of thinking about two syntaxes on the fly. Let's not go there, right? I mean, I could figure this out, but this will take too long. I'm essentially referring to ad hoc polymorphism and type classes, right? And the difference being that you would have this syntax instead. You would say filter, pass the predicate function, and then pass the excess, as opposed to saying excess.filter and then pass the predicate function. So yeah, so okay, so filter is a so there's an instance of filterable that operates on things of type x's, of the particular type of x's, right? And that's done through pattern matching. Sorry, that's what I should say, something along those lines. But again, this is completely irrelevant to learning this thing. It's just I'm trying to draw some analogies to more classic functional languages such as Haskell, for example. But okay, let's move on. What was I actually saying? Well, we were reading through this definition, so let's continue reading through the definition. So right, we were saying that what they're expressing here is essentially the same thing that we were expressing in the beginning, but they are expressing it in terms of filterable, of this general idea of something that's filterable as opposed to just a particular list. So if you think very carefully about the language that they're using here, because it's actually very good, right? So what they're saying is that it takes a predicate and a filterable and returns a new filterable of the same type containing the members of the given filterable which satisfy the given predicate, right? That's the same thing that we were saying, but we were saying in terms of lists. So we say when you give a predicate and you give a list, then you get back a new list that contains all the items from the old list that satisfy the predicate, but not the ones that don't, right? So like when we had greater than 5, then we get back all the things greater than 5, but we don't get back anything less than 5. So okay. Filterable objects include plain objects or any object that has a method that has a filter method such as array. So what they're saying is that all of the things in actually, and this is very clear when they're saying this, dispatches to the filter method of the second argument if present. So array, as we talked about before, right? If we don't think about Ramda, if we just say console log Array.prototype.filter, I assume that we get a function back. Let's try this. Yeah, we get a filter function, right? So what we're checking now is that in native JavaScript, there is a filter function. However, I'm not sure. What if we do object.prototype.filter? Do we get a filter function back then? No, right? So there is no filter function for objects in native JavaScript. I would assume, right, from just doing this very small test. But it would seem to me that would make sense. But however, they do say filterable objects include plain objects or any object that has a filter method. So probably Ramda has an implementation that allows you to filter objects. Now we'll have to see what that how that works, right? Like whether you can actually see that example here, right? So I'm just thinking, yeah, that works on a value level rather than a key value pair level. So it's like when you're mapping over an object, for example, if you use the map function in Ramda and you're mapping over an object, then you're mapping over the values in that object and you're not actually ever seeing the keys. But if you want to see the keys, you have to use that other function that we've used some other time, which is something like map accum, let's look at that, map accum. Yeah, map accum, right? No. Sorry. I'm confusing. Map obj. Yes, map obj indexed. That's what I'm talking about. Sorry, map accum is something else, right? That's like something like a mix of map and reduce for objects, but whatever. Or not necessarily for objects even. Sorry, I'm just being confused. That's a different function. What I was talking about is a map obj indexed. So anyways, okay. That's that, right? And then the last thing that they have here in the documentation is that they're saying acts as a transducer if a transformer is given a list position. Now, as I've said before, right, I don't fully understand transducers, so we're going to talk about transducers when we get to transducers. So when we're at T, which hopefully gives me a bunch of time to learn a bit more about transducers before we get there. But supposedly you can also use filter here as a transducer. Okay, and then they're also saying see also reject, which we've looked at, transduce, which we just talked about now, and then add index. Let's click add index. I'm wondering why. So add index, yeah, okay. So actually there are two ways of solving the problem that I outlined now, right? I said if you want to filter and you don't only care about the object values, but you also care about the keys in that object and you want to filter over that, then you can either use map obj indexed, or you can add index. You can use the add index function. And then you can see here that if you, they have an example here. And I mean, since this is on A, we must have talked about this in another episode. Sorry, there are so many episodes, so I keep forgetting what we've talked about. But you can wrap or you can apply the function addIndex to, for example, map, and then you have a mapper, or not a mapper, you have an implementation of map that when you supply a mapper to it, then that when you supply a function that you want to map, then that function will take 2 arguments instead of 1 argument. So it will be able to access both the value and the index instead of only, as opposed to only the value. And the same thing here then. I assume that they're saying addIndex here because then you can filter not just on the basis of values, but also on the basis of keys, because your filter function, if you don't use addIndex, will just take the value. Like the predicate will only take the value. It will be a unary function. But if you want to have binary predicates where you're checking both, or like where your the truthiness of your predicate is based not only on the value but also potentially on the key, then you can have a binary predicate. And to get that binary predicate to work, or to rather to ensure that your binary predicate's second argument, in other words the key, or maybe it's the first, I don't know, we'll have to see, is actually passed, then you have to use addIndex. You have to wrap filter in addIndex. But okay, anyways, let's actually look at some code now. That was a lot of talking. So how to transform this sort of native JavaScript version into something that uses Ramda. So what we do is just this, console log, and then we say, instead of saying x's.filter, we say r.filter. We pass the predicate, so let's say p, and then we pass the x's. Right? And if I console log that, we should get exactly the same thing in these 2 scenarios. And you can see we do, right? So that works. But of course, the power is that you can curry this, right? So you could say r.filter using this predicate, and then you pass the x's to that function, right? So that means you could have, you could define, right? It's like, let's say we define a new constant called everything above 5, right? This is a stupid filter, but I mean, you get the point, right? And then we could say r.filter x is, or let's do this instead. Let's say only positives, and then we filter such that every x has to be greater than 0, or actually let's say greater or equal than 0, greater than or equal to 0, and I'm not sure if that, yeah, I guess that would count as a positive number as well, because it's like positive 0. And then let's add in some negatives here, right, so that we have something to work with, like so, whoops, like so. And then I guess let's remove that other old predicate so that we're only thinking about one thing at a time. So and then let's say, so what do we do? Now we have this filter only positives, and it's a partially applied function that only expects the data and not a predicate. So then we can apply that function only positives, and we apply that to the x's, and then we should get only the positives out of the x's back, right? And as you can see, we do, right? We have like -3 is not in there, -88, -12, and -2. They're not in that second list, right? So that seems to work super duper good. Okay, so and that's again, like, that's the power of doing these filters. And of course, like, you can also compose them as usual. So I'm sorry, I shouldn't get long-winded, but of course you could do these things, such as let's say you have this filter from before. You've defined this only positives filter, and then maybe you've defined this like no negatives. No, sorry, no, yeah, that was the same thing. no zeros, and then let's define that as r dot filter x, where x is not 0, and then you could of course pipe. So then you could say r.pipe, first do only positives, and then do no zeros, and then we're passing in the x's, right? Close the console log. Let's look at that, right? Then we're also getting rid of the zeros. Right, then you could keep piping a bunch of functions. Now let's also talk about reject, right? So when we have this no zeros, we could also implement that as a reject. I mean, you can always implement a filter as a reject and vice versa, right? It's like you can always express sort of a positive condition as a negative condition at the as its inverse, I guess. Yeah, but so no zeros could be implemented as reject, such that for some x, if that x is equal to is equal to 0, then that thing should be rejected, right? This would work the same way. You can see we also reject zeros now. So now we're rejecting zeros as opposed to accepting non-zeros, right? But I mean, in terms of in terms of the way they map values to, like in terms of domain and codomain, or domain and image, it's the same function, right? It's like we're mapping the same input to the same output. Okay. I mean, comparing across the two functions, or comparing across the reject implementation and the filter implementation of no zeros. Okay, so that's that. I think you're probably totally seeing how this works, right? So let's move on to something a bit more interesting. So let's think about this idea of what it means to be a filterable. I'm not seeing anything about the Fantasyland specification here, so I don't actually know if they specification, can't spell and talk at the same time. So I'm not sure if they actually support Fantasyland filterables, or whether they just support something that implements the filterable interface. But at least let's use the Fantasyland specification to understand what it means to be a filterable function, or sorry, a filterable structure. So let's read here, right? A filterable has these three laws, and it only actually needs to implement the filter method. And then, yeah, this is just a description of the filter method. And then the next section is functor, right? So there are only these three laws, and then there's filter. And what are they saying here, right? Actually, I mean, we've skipped the laws in the other ones to keep things quite short, right? And I'm going to do a series on Fantasyland specification in the future, so be sure to subscribe so that you won't miss that upcoming series, right? But yeah, there are three laws: distributivity, identity, and annihilation, right? And so, like, I mean, these are as usual, or as always, like, they're actually, if you think about them, fairly self-evident. It's like, if you have this list of x's, like here they say v. If you have this value and you filter this value, and your predicate is a tautology, right? Your predicate is this thing that always returns true, like it's the true constant. Then that's the same thing as v. Right? If you have a value and you say filter and accept everything, then you should get back the same value back, of course, right? And for reject, that would be the opposite, right? It's like, if you have a structure such as a list, and then you reject, but you reject nothing, you reject using the predicate false, like the false constant, then of course you should get back the same thing. Then it's equivalent to identity. Okay, so we could think about that. Yeah, that's actually, as a side note, right? It's like, in a functional sense, right? It's like, if you have the function filter, like this, right? R.filter on R.always, true, right? This thing is like actually equivalent to R.identity. That's what they're saying with that law. But anyways, I mean, you can, I think that's what they're saying. But you can read through those if you want to, right? Let's actually just dive into this. So what they're saying here, let's look at the type definition. This is essentially, I guess, the same type definition as we have. No, sorry, this is of course not essentially the same type definition as they have in Ramda, because here they're specifying using object syntax, and in Ramda we have this sort of function syntax where the object comes in the end. But so here they're saying that for something to be filterable, it needs to be implementing the method filter. And who implements the method filter? Well, assuming that f is filterable, then if we have some, let's call it a, and that this a is filterable, right? Then it needs to implement the method filterable such that when given a function from a to boolean, again, this is the predicate, it will return a new filterable containing a's, right? So think about this as that. Let's say, replace the word f for list here. So then they're saying assuming that list is filterable, and assuming that you have a particular list containing something of type called a, right? You could replace a for ints here. So you have a list of ints. If you then call the method filter on this list, and you provide it a predicate, that, like a function that maps from int to boolean, right? From int to either true or false, then you will get back a new list of integers. You will get back a new f of a. So that's sort of the same thing as the Ramda. Is just, again, like object syntax versus, let's say, function style or function syntax. Or, I mean, I shouldn't say syntax. Let's say, I mean, it is syntax, but like function style or object style. Let's think about it that way. Okay. And yeah, we need to pass a predicate. The predicate must be a function. If the predicate is not a function, right? If the variable passed, or if the argument passed is not a function, the behavior is unspecified. And for P to be a predicate, it must return true or false. and if it returns any other value, it's unspecified. So actually, it seems that the Fantasyland specification is actually pretty strict, because they're not saying truthy or falsy. They're saying it must return true or false, and behavior is unspecified if it's truthy or falsy. But anyways, and the filter must return a value of the same filterable, which makes sense, right? It's like if you would filter an array and you would get back an object, you're like, well, this makes no sense, right? Or it's like if you filter an object and you get back an array, and you're like, well, but how am I supposed to find this predictable, right? That just doesn't make any sense. So you have to return back something of the same type. So let's try to build our own filterable. And I think actually let's use the maybe type. So I don't know how maybe types are usually implemented in JavaScript, but let's just try it out, right? Like, let's say what is so maybe is something that needs to have, let's use the terminology just and nothing. And maybe I've talked about maybe before, but maybe is this, I'm just not going to be long-winded. I'm going to be sort of try to be sort of dense, right? But maybe is this this idea where you can express something which is either a value or it's not a value. So it's like a nullable type. I think it's like, I mean, it's in C# or in some languages you have something like, instead of saying int, you could say int question mark. So like if you're saying, I'm not sure, I can't remember if ints can be null in C#. I think maybe they can't, right? I don't know. Let's say that ints can't be null. So if ints can't be null in C#, then you could say int question mark to express that maybe I have an int, maybe I don't. But then it's very explicit that you need to handle that. Now, that's not really, if I'm not mistaken, that's not really entirely as powerful as separating them using this sort of idea of tagged unions. So, yeah, I was just thinking whether I was saying that correctly. It is tagged unions, right? Tagged some type. No. Wait. Yeah, let's not think about. Please correct me in the comments. I think that's correct, right? It's like, oh yeah. Let's just to ensure that I'm not saying this incorrectly. Tagged union. Yeah, variant record choice type. Yeah. Okay. So tagged union, also known as a sum type. Yeah, sorry, of course. My bad. Yeah. Never mind. So if that didn't make any sense, don't worry, right? So a maybe type can be either just something or it can be nothing, right? So let's build some kind of implementation of maybe, right? So how would we do that? Let's say if you have what are we going to do? Let's say we have the function, or let's say okay. So let's say we have a structure. We have a structure called maybe, and then maybe dot just is a function that constructs a maybe. So if you say just, you would pass some x, and then you would say, then we maybe store that x, right? So this dot x is the x that we passed in, and if you say maybe dot nothing, then that's a function that doesn't take a value because you're just constructing nothing, right? And then that's not a problem. Or then we just do this, right? It's like we're saying you get back a new function. But okay, but then actually we need to get back a new function, and then we need to specify something on the prototype of that. So maybe I should have thought about how maybes are conventionally implemented in JavaScript before I started to record this video. Let me just, this would be interesting. Let me try something, and then we'll just Google and see if the implementation that I end up with is sort of conventional or not. So again, like in Haskell, I would use pattern matching, but here we have to actually do, we have to use, I mean, I'm not trying to say, polymorphic dispatch? I mean, we have to use, no, that's probably incorrectly stated of me. We have to use polymorphism at least, right? To differentiate between justs and between nothings. So maybe I actually need sort of two types, and we should think about these as subtypes of maybe. Actually, like that's actually a way of doing it, which is that would be very obvious, right? So I don't think I would actually do this if I built the type, but let's maybe actually use subtypes because that would That's going to be extremely clear if you're from an OOP background. So let's say inheritance JavaScript. Let me just get the syntax right. So can I do class inheritance, yeah, classes. No, okay, so you have to do, okay, so you can't really do that. It's not as obvious. So then you have to do it on the, yeah, okay, so no worries. So so then maybe a maybe is implicit, right? So maybe just as a fun, yeah, okay. Sorry. Let's not use classes. I'm sorry, you could probably use classes, but I'm not familiar enough with JavaScript classes in order to do it. So what we need to do is something like this. We need to say, if you construct a nothing, whoops, then that thing is going to have a prototype. And on that, we're going to say that there's a filter method. And that filter method is going to take a function, or sorry, it's going to be a function. That filter method is going to be a function. And if you invoke the filter method, you can pass it a function, and that function is a predicate. So let's call that predicate P. And the thing is that if you have nothing, then there's nothing to filter. So then we should just return the same thing. We should just return this. But if you have a just, right, then let's say maybe dot just, that also on its prototype has a filter function. And that filter function can also take a predicate, of course, because it's like we're saying, we're claiming that maybe corresponds to the idea of being filterable, which means that every way of constructing a maybe needs to support or needs to implement a filter method. Sorry, I said filter function before, but I meant filter method. But that's slightly different, because what that does is that it applies the predicate. So here we need to branch. We need to say, okay, well, apply the predicate to the value inside of this maybe, because now we actually have a value. So apply the predicate to this particular maybe. And if the predicate is true, or sorry, if to the particular value inside of this just, and if the predicate is true, then what we want to do is we want to keep this value. So then we should return actually the same thing, right? Then it's identity. We're returning the same thing. Else, we should get rid of this thing, which means that we should return a new nothing, right? So maybe dot nothing, like that, right? And let's maybe then condense this implementation. Let's just rewrite that as using a ternary expression. So we would say return p all over this x. If that's true, then this, else it's maybe dot nothing, right? So same thing, I'm just expressing that on one line instead. Okay, so I would guess this would actually work. Maybe I'm wrong, you know? We'll see. So the reason we would do this, let's forget about the x's, right? Let's forget about the list. So now we're talking about filtering maybes. By the way, I don't know if theoretically people implement filter implement filter for maybes this way. Maybe there's another way. This just seemed like intuitively sensible for me. So what I'm saying then is that, let's say you have, instead of I mean, we could call it x's now as well, but now it's actually maybe, so let's just maybe call it x, right? So, and let's just then say that we have the value, let's say 10, inside a just, right? Let's just, maybe let's first make sure that I don't have syntax errors. So we need to put this stuff in the end and declare the maybes first, right? So let's just try to run that to see if that blows up. No, so that doesn't blow up. That's good, okay. No, but why did we get undefined back? Wait, maybe, well, if I console log maybe, and then I console log maybe dot just, that's a function, and if I then console log x, is a function, wait, am I messing this up? No, wait. Maybe dot just is a function that sets. Wow, I just got very confused. Isn't that the, so if I, like, do we have a filter method on x? No, because x is undefined. Woof, I just got heavily confused. Isn't this the usual way we do this? We say, I want to have this object that I can, like, let's say I have an animal that I can construct, and that thing is a function, and then you can define things on the prototype of animal. So let's say speak is a function defined on an animal. Let's say, so instead of console logging all of this stuff, I would console log animal. Yeah, sorry, it's new. Oof, my bad. So back to here. Okay, sorry, just I'm forgetting about JavaScript. So what I need to say is I need to say new maybe.just, and I pass in 10, right? Then we have the filter function on that x, and if I just console log the x, you can see, yeah, we have a maybe. Okay, so what I'm saying is this: if you have, let's construct a few variables, right? We have a const x. Let's say we have const y. Const y is a new maybe dot nothing. And const z is a new maybe dot just 5, let's say, right? If I now console log all of these, so let's console log x and then y and then z, y and then z. So let's save that and let's run it. Then you can see we get back, in the first case, we get back a structure containing the value 10. Then we get back an empty structure. And then we get, sorry, I should have said object instead of structure. And then in the last one, we get back an object containing the number 5. However, these things are have prototypes that have methods. Can I console log the prototypes like this? No. But that means that we have, yeah, we could probably ask for like all properties of or whatever. But now we happen to know that they also implement the filter function. So I can console log the what am I doing? Like so. The filter function, or the filter method of all of these, right? So notice how these all, like if I say dot filter on these, they return a function, and these are the methods, and we're going to use polymorphism, or we're going to use polymorphism when we call these filter functions. Or like what I mean is that if you don't know whether you have this x or whether you have this y or this z, you can construct a new function that takes something that is a maybe and expect that thing implements filter, which is then what the Ramda function filter does. It expects that your structure, your object is implementing the filter method, because if it does, it can dynamically dispatch to that, and then it will do different things depending on what the implementation of that filter method is. So I don't think I'm making a whole lot of sense. What I mean is this: what if we now actually invoke the filter method and we pass some particular predicate? Let's define some predicate. Let's say that the predicate is x is greater than 5, right? So a function where when given some x, returns true if x is greater than 5 and false otherwise. What do we get back from these things, right? If we invoke the filter function and we pass, actually, what am I doing? Like so, let's do all of them at the same time. If I pass the predicate to these filter functions, let's think about that, right? In the first one, we should get a just containing 10, right? Because 10 is greater than, because it contained the value from the beginning, and 10 is greater than 5. In the second one, I should just get nothing back, because I didn't have anything from the beginning. So like there's nothing to filter, I'll just get nothing back. In the third case, I should also actually get nothing back, because we're saying I want to filter on this thing being greater than 5, but even though I had a value before, the value I had was 5, and 5 is not greater than 5, which means that we will get back nothing as per this implementation that we made here, right? That's what we're saying. When you have a value, that's what we said in this implementation. And again, I don't know if this is the conventional implementation for a maybe, but it just seems to make sense, right? It's like, well, if you have a value, you can filter, and if you do filter, then you should get back. Or like if the predicate fails, then what can we do? Like we don't want to return the value because you've just rejected the value. So then we return nothing. So let's see if that's what we get. Just 10, nothing, and then nothing. Actually here we get undefined. So that's a bit problematic. Let's look at that in just a moment. Okay, it's probably because I forgot the new keyword again, right? But in the top one, that seems fine. This looks like a just. And the second one looks fine as well, and also it contains the same value, which is 10, right? And also the second one looks fine because it contains because it looks like a nothing. It just contains nothing. It's an object that contains nothing. And the last one looks problematic, right? But that's probably here because I missed the keyword new. So let's try again after having specified that. Yeah, and that looks fine as well, right? Maybe we could do this just to say just to maybe make this a bit more clear. So when we construct a just, let's say that we set a type property. We set the property type to just. This is just, I mean, we're just doing this for the sake of clarity. And then here we're gonna say, no, sorry, not for filter. And then when we construct a nothing, then we actually need an implementation here. Then we're gonna say this dot type is a nothing. Nothing, right? And then let's run that again. Then you can see, right? We had, so maybe we should actually even do this. Let's first console log x, and console log some lines. So let's do some lines between these, and then, and then here let's console log y, and then here let's console log z. So first we're looking at the original value, and then we're looking at the filtered value, right? And remember, the predicate is greater than 5. So first we have a just containing 10. Whoops. We begin with a just containing 10, and we get back a just containing 10, right? When applying the predicate greater than 5, or when filtering when filtering using the predicate greater than 5. And here we started with a nothing, and then we get back a nothing because that's false, right? It's like the predicate is failing. And or that the predicate returns false because it doesn't satisfy the criteria. Or no, sorry, that's not true. That was incorrect. It's not that the predicate returns false. The predicate is not applied because we don't have anything. And you can, I mean, if you feel like this doesn't make any sense, you can think of this as empty array, right? Like, you can filter an empty array. That's not a nonsensical thing to do. You can take an empty array and then you can ask that to filter using an arbitrary predicate. You're still going to get back an empty array, right? But that's totally fine. It's syntactically valid and it's semantically valid to try to filter that thing because you don't know. Like, maybe it has some value, maybe it doesn't. And that's the thing here, right? Like, there needs to be an implementation for when you don't have anything. Whoops, now I accidentally pasted in some stuff. There needs to be an implementation for when you don't have anything, right? And that's the nothing. So you can filter a nothing, but then you just get back nothing. You get back an empty array, right? But here's the really interesting scenario. If we had a maybe, but rather more concretely, we had the just, and this just contained the value 5, then when we apply the predicate will actually fail. And if the predicate fails, then we can't return that just, right? Because then it's like, if we had the array and this was an item containing the number 5, then that item should not be returned because, I mean, that item should be rejected. And now in a maybe, we just have a single item. So that means, like, you can think of this as that we had an array of length 1 containing only one item, which is 5. But then we rejected that value because the predicate failed, which means that we should return an empty array. So we return the empty array, which in our case then is the nothing structure, right? So yeah, hopefully that sort of makes sense. I don't want to dive too deep into this, and again, we're gonna talk a lot more about these things when we look at the Fantasyland specification. So in that series. So again, remember to subscribe if you're interested in that, and let me know in the comments if you have any questions. Now, clearly, maybe this is an exercise for the reader. Yeah, like, of course you could write this, the maybe structure that we wrote here using classes, right? So I guess instead of using subtyping, as I talked about before, I forgot to think about the fact that we're now in a dynamically typed language, so you could just think about duck typing. So you could actually just maybe define the class just, right? And you would define the class nothing. And then maybe you would sort of want to namespace these, so it's like maybe dot just. I don't know if this is actually valid syntax, right? But you maybe want to namespace the just class onto some other structure so that you know that you're constructing a maybe, because otherwise it's not very evident, and also you're polluting the namespace with using a word that you might want to use some other time. But anyways, hopefully that makes sense. Let me know in the comments if you have any questions. And as usual, I find it interesting that we're managing to talk a bit about stuff sort of on the fringes and not just stay into the actual just implementation of filter for Ramda. Sorry, I forgot to say. What I should say is, of course, that notice that this is the output that we have. Now, since we have a structure that implements filter, that means that we can take that structure and we can pass that to Ramda's filter. So instead of doing this, x.filter, and then passing the predicate using this sort of object notation, we could also say R.filter, use Ramda's filter, pass first the predicate, and then pass my x. And then we should get back the same thing. Right? Let's do the same thing for y and for z. So instead of x here we have y, and instead of x here we have z, and then we should get back the same result. So let's look at that, and you can see we do just 10. So these two are these two return values are the same. We get nothing in both of these cases because those are the same, and then we get nothing in those two cases because, again, like, the implementation actually worked. Like, Ramda is actually delegating to our implementation of filter, and we have a sensible implementation of filter. So then you can use all of the good stuff in Ramda, where you can pipe and you can compose and you can partially apply and all of that stuff. And again, think about the fact that you don't necessarily have to think about this as something that only applies to a list or a maybe, or like these sort of, or objects, right? Like these perhaps simple structures. You can filter anything that you like. You can implement filter for anything that you deem to be filterable, as long as it follows the laws of what it means to be filterable. So maybe have a look at the Fantasyland specification. But if, like, you can have this arbitrary thing like a person, right? Or like a user object. You could say user object is filterable. Now maybe a user object is a bit tricky because users maybe then contain a bunch of properties and then it's not obvious what you should filter on. But maybe it's not, right? Maybe you would actually say that a user is filterable, and then it's just sort of this, like, you just turn this user into a string, and then the predicate is sort of matching whether the user contains that string or not. But, you know, maybe this isn't really... No, sorry, actually that's a particularly bad example, right? That's a particularly bad example. That's not what we should think about, because the box needs to be parametrically polymorphic, right? Sorry, I'm understanding if I maybe don't make any sense. What I mean is that a maybe can wrap any value, right? A maybe could wrap an array or an int or a string or like a Boolean or whatever, right? A list could contain any kind of value. A list could contain a Boolean or a bunch of Booleans, a bunch of integers, a bunch of numbers, a bunch of strings, a bunch of objects, a bunch of whatevers, right? It's parametrically polymorphic. It's like generics in C#. It could contain anything. Now, person object couldn't really contain anything, so then it's a bit strange, because then we're saying like it's this thing that's filterable. Yeah, but actually, why not, right? Oof, I'm on thin ice, so I'm gonna quit this now. I think actually person could be a good candidate for a filter, or rather, I shouldn't say a good candidate. I actually think it's still a bad candidate because its responsibility is too wide. But I think, like, generally you could implement filter for a person class. Let me know what you think in the comments. Could we do that, or could we not do that? And again, is that a good idea or is that not a good idea? Anyways, thanks a ton for watching. I'm glad to have you along on this journey. Remember to subscribe. Share this video with somebody who you think might appreciate this video, maybe with somebody who's learning functional programming, maybe with somebody who needs to learn about the function filter. Thanks a ton for watching, and I will see you in the next one.